Hello, everybody. I'm just trying to gauge how far it goes. And is that glare bothering you? Whoever of my elements are here, can you tell me if that glare is bothering you? Can you hear me, elements? Hello, Kash. Is this glare bothering or is that okay? No, not really. Okay. Thanks, KK. So we're here for Big Idea 1 review session 1. How's your weekend going? Did you all do practice quiz 3? Can you move the camera up or the board down? It's cut off. Yes, Matthew. Here you go. How is that? You're welcome. Okay, so I am thinking today might be review the concept for Big Idea 1 and then going over the quiz 3 kind of day, and that we save going over the practice test for Big Idea 1 tomorrow. That will give everybody enough time, because your test is day after tomorrow, to take the practice test and not give out the answers to some of you. So I'm going to wait on practice test 1 to go over tomorrow. Same time, same place, 8 to 9 p.m. And tomorrow you'll also have in class time to work on the Big Idea 1 practice test and do the review. Do not forget to do the content review. You must review the content. So let me start with content review. And are there any concepts that you have trouble with in Big Idea 1? Remember, you have a playlist of Unit 1, Quiz 1, 2, and 3 review, which is time-stamped. And I've created this playlist and added it to the calendar, so you can go to the specific content where you have problem. Do not forget to review the labs. And the labs in the first Big Idea, if my memory serves me right, are Green Chem lab, there was Hydrates lab, then there was Spectrophotometry lab, and then there was Titration lab. Did I miss out on any of the labs that we did? Hello, Suraj. So I think these are all the labs I can think of, and then there are a bunch of concepts. All the 3 units concepts, 20 learning objectives. First 20 learning objectives is what this Big Idea test will be about. So if there are any concepts that you're confused about and you'd like me to troubleshoot, now is your time to ask me. Hello, Aditya. Everybody, hello. Claire, it's nice to see who all are here. Okay, gravimetrics. KK says he wants me to go over gravimetrics. KK, can I pose a question for you? Is there any specific part of gravimetrics that you don't get, or do you want me to kind of just summarize gravimetrics to you? Okay, Ritu, I saw the translational, vibrational, and rotational energy. I will do that. I was just waiting for KK to respond if he has a specific question on gravimetrics as he reviewed it, or does he want me to just go over it one more time? Okay, so gravimetrics is a methodology. I'm looking for, wait, I get distracted easily. I have my pen here. Okay, gravimetrics is a methodology using which you can find either molarity or amount of a particular substance in a solution by precipitating it. So let's say you have a solution of, let's say, lead nitrate. So there will be lead ions in here, right? And then there will be nitrate ions in here. I'm just making one formula unit here. And I want to know how much lead is in there. If you look at the solution, it's just going to look like water because we can't see lead ions. What we can do is we can find an ion or an ionic compound which can selectively precipitate lead out. So I know one such compound is sulfate, but I can take an ion by itself. So let's say I added sodium sulfate to it. What this sulfate will do, it will selectively go and bind with lead. And what you will see is Pb2 plus and SO4 2 minus precipitates at the bottom, settles down as a solid. If you recall from the class, we precipitated it. And then we have nitrates floating around, and we have the sodium from here floating around. We don't care for these, but they're there in the solution. Now, what if we filtered it? Poured it down a funnel with a filter paper on it. What's going to happen? This lead sulfate, Pb2 plus, SO4 2 minus, will get stuck on the filter paper. And if we have weighed it, what we can get is grams of PbSO4. Now, from grams of PbSO4, the way ultimately what we want is grams of Pb ions, right? So we can get how much of Pb was in there. But there is no gram to gram relationship between PbSO4 and Pb. So what we're going to do is using molar mass, we're going to first convert gram of PbSO4 to moles of PbSO4. And once we convert moles of PbSO4, we know that there is a 1:1 ratio. In 1 mole of PbSO4, 1 mole of Pb, we can get Pb. And then from that, using molar mass of Pb this time, we can get grams of Pb. So gravimetrics problem could be simple, and they could just ask you how many grams of lead was present in the solution. But they can always ask you, what was the percent purity? If they gave you, there was like, this is solution, so they will give you the amount of solution and they'll say that it's got 2 ions in it, or they may give you a solid, but the methodology remains the same. You first dissolve something, precipitate it out, and using the mole ratios, then you can figure out how much it was. That is summary of gravimetrics. Rania, I will timestamp it. I will get to it once my video is done processing. Sometimes video takes time, so I'm not sure if I'll timestamp now or in the morning. If it gets processed in time, then I'll timestamp it now. So rotational, vibrational, and translational energy. And what you need to know about these is vibration means if these are molecules, they're just vibrating back and forth in their space. So it's a smallest movement, okay? If these are two molecules, they're just vibrating in their own space, right? Wow, that's like a funny face. Rotation is these molecules, in addition to vibrating in its own place, they are rotating, right? Spinning. And translation is this molecule was here and now it goes and moves here. So it's a larger movement. Translational energy generally is associated, this is the largest energy. Rotational is second largest. And vibrational is smallest. So when you're talking about the lowest amount of energy, you're talking vibrational or rotational. But if you're talking UV, or if you're talking electron transition from nucleus, from the energy level closer to nucleus to higher, then you're talking about translational energy. And that's how much you need to know in this content. Okay, so Ritu and there was somebody else, I think Rania, both asked about translational, rotational. You got that. Suraj. So regarding Green Chem Lab, we set up the equation as X times. Yes, Suraj, that is correct. In Green Chemistry Lab, we set up moles, or we set up mass of total mass lost is mass of CO2 plus mass of water, because both of these are formed in 1 mole ratio. So it's n moles of CO2, right, times molar mass of CO2 plus n moles of water times molar mass of water. Because if you remember, it was 2 NaHCO3 solid gives you Na2CO3 solid plus H2O gas plus CO2 gas. So if you notice here, I know you're doing math in your head, but in moles, math doesn't add up. There were 2 moles of this making 1 mole and 1 mole and 1 mole. So from 2 moles, you're getting 3 moles. So moles don't add up in a chemical reaction. Masses do. So yes, Suraj, that is correct. KK. Well, KK, I am not in class tomorrow, you know that, but I can do the practice problem on gravimetrics with you a little later. So write out which problem you want me to do. I did print it out. I thought maybe some of you might have questions on it. I have it here. So tell me which problem and I'll do it. You guys welcome Aditya and Ritu. Okay, so Shitaro, which particulate on titration lab? So we did HCl NaOH titration, right? So let me go over the titration lab particulate level drawings. So in this lab, you first made NaOH solution, right, starting with either solid NaOH or starting with 3 molar NaOH. So in this part, you have no acid. So your particulate level drawings will just should have either solid NaOH, and as you draw it, make sure you have opposite charges. Or if you have aqueous NaOH and you're diluting, then 3 molar will have little bit more Na and OH separated. Whether you draw water molecules around it or not is up to you. I would keep them separated. So I drew 3 to represent 3 molar. And as I am diluting it to 1 molar, I will only make in the same field of view 1 Na plus and 1 OH minus. So that tells me in the same field of view 3 to 1 ratio. This drawing looks smaller, but you have to draw them in the same field of view. So that was first part. Second part, you are standardizing your standard NaOH, which may not be 100%. So this is around 0.1 molar NaOH. And here you will draw Na plus, OH minus, that is in here. And in the Erlenmeyer flask, you have KHP. So I would be okay if you just drew KHP as a solid acid, or if you did K plus HP minus, either works for me. And then some water in there. And then at least 1 indicator. Then the third step is important. It's equivalence point. At equivalence point, actually the third step is not equivalence point. Let's start now. I'm going to erase this elements. The third step is you've now taken the unknown HCl in the Erlenmeyer flask. So now you have this standardized standard NaOH. So we know its exact molarity, maybe 0.0998 molarity. Okay, I'm just making up the number. And now what you have here in Erlenmeyer flask is the unknown HCl. Okay, and in here you put, wow, I got pink. So you have phenolphthalein, which is not pink yet. In the next one this is initially. And then at equivalence point, you will have neither HCl nor NaOH, because NaOH will completely combine with HCl and will convert to NaCl and water. So what you will see is Na plus, Cl minus, and H2O all in a 1-to-1 mole ratio. And then past equivalence point, you would have the same drawing, but now there would be 1 more drop of NaOH. So you should have at least 1 more Na plus and OH minus here, because now you're going past the equivalence point. So you got it, Shitaro. Here, what do you agree with Sean? Shivani? Is it like draw both at equivalence and past equivalence? I drew both. Anusha. Oh, you do have to standardize the solid NaOH solution, definitely. So whether you made, Anusha, your solution from solid NaOH or you diluted 3 molar, in either case, you would standardize it with KHP. You need to do it in both cases. You do have to standardize solid NaOH. I just drew as 1, so I hope that's clear. Navya, how to find the structure of a compound like nitrous oxide using mass spectrometry. So Navya, how you can find the structure of a compound like N2O using mass spectrometry is, let's say if we know its formula is N2O. Now it could be that N is attached to N and then O, or it could be that N is attached to O and then O's in between or O's at the end. Now, you know mass spectrometry breaks the bonds randomly. So there are various options. No bonds get broken in either case. If no bonds get broken, then it's 28 plus 16, 44 grams, right? Or 40, you'll see a peak at 44 AMU, not grams. You'll see a peak at 44 here. If all bonds get broken, you'll have a 14 and a 14, right? And a 16 peak. If all bonds get broken, you'll have a 14 and a 14 and a 16. Now, if bond 1 gets broken only, so what will that look like if bond 1 gets broken? N separately and NO separately, right? In that case, what is the mass? 14 and 30, right? Next scenario is this gets broken. So you have NN and then O. So this is 28 and this is 16. Now, if you go here, this gets broken. So you get N and NO. So that is 14 and then 30. If this gets broken, you again get 14 and 30. There is no way you can get a component of 28 because for this to weigh 28, N has to be attached to N. And that's how you figure out the structure, whether N is attached to N or N is attached to O. That was Navya Suraj. Okay. KK number 2 from LO 1.19, which talks about 35 mils at the beginning. (1.19) So do you have your calculator handy? Because I don't. Take out a calculator so you can do calculations for me. 14, 16, 19 gravimetrics. So let's do the problem here. This is LO 1.19 from extra practice problems. Okay. You want to analyze a silver nitrate solution. You could add HCl. So you want to analyze AgNO3, right? And you add HCl to it. And when you add HCl, what precipitate is AgCl. They give you this, right? When you write solid, you mean a precipitate. What volume of this 0.150 molarity HCl should be added to precipitate silver ions from 15 mils of 0.2 molar silver nitrate? Now, in this case, KK, one thing that's not given here, which you will get on the quiz, is the reaction between AgNO3 and HCl. So Ag spells that. So AgNO3 plus HCl, this will be given to you. The one I'm writing in blue gives you AgCl plus HNO3. So now you know that Ag and Cl react in a 1-to-1 mole ratio to make AgCl. So the thought process is going to be we are going to, if we multiply molarity by volume, we'll get moles of AgNO3 here, right? How? By multiplying 0.015 by 0.200. Once we get moles of AgNO3, right, you know that 1 mole of AgNO3 makes 1 mole of AgCl, right? So moles of AgNO3 are equal to moles of AgCl. Once you have moles of AgCl, or you could have gone straight from here to here also. 1 mole of AgNO3, you don't even need to go to AgCl. 1 mole of AgNO3 reacts with 1 mole of HCl. So this will be equal to moles of HCl. And mole of HCl is molarity times volume. You already know this. Molarity is given to you. You can figure out the volume. So I think the problem there was the reaction wasn't given, but it'll be given to you. Part B of it says, are you guys okay with that? Oh my God, there's so many. Okay, wait. I don't want to miss anyone. Kesivani, you're welcome. Raghav. Oh, Raghav, your question, how would calibrating a spectrophotometer with tap water instead of DI water change the readings? There might be some ions in it. And if those ions absorb light, which is highly unlikely, because if those ions absorb light, they would be colored. But what is present in addition to ions in tap water is sometimes some little small particles that your eye cannot see. And if they absorb the light, then your reading would be higher. So depending on what is in your tap water, but you can be sure there are some particulate things in your tap water. It's not perfectly clear. So it'll increase your perceived concentration of your solution, Raghav. Hello, Eugene. What is the difference between endpoint and equivalent point? Okay, so KK, I did part A here, assuming you just needed part A. If you need me to do B and C, you will let me know, okay? Okay, Eugene, the difference between endpoint and equivalence point. So let's say we were doing HCl titration with NaOH, right? We know they react in a 1-to-1 mole ratio. So when their moles become equal, we will not have this or this acid or base. It would have converted completely to NaCl, salt, and water. This point is called equivalence point. At this point, however, phenolphthalein, which is our indicator, remains colorless because at pH of 7, which is what the pH is when acid-base titration, strong acid, strong base titrations at equivalence point, it'll remain colorless. But when you add one more drop of NaOH, then what happens in addition to this? There's also Na plus and OH minus in the solution. This OH minus acts as a base, and when there is a base, in presence of this base, this phenolphthalein turns pink. And this is what we call endpoint, because endpoint is what our eye can see, equivalence point our eye cannot see. So endpoint follows equivalence point by one more drop of the base. And we take that error because we have no better solutions. Yes, Joseph, you were right. Endpoint is after equivalence point, Arushi. Yeah, good job. Very good. Aya, can I go over 10D and E in practice quiz 3? Yes, Aya, I can. 10D and E. So before I go to practice quiz, I see a lot of you are moving now. Raghav, you're welcome. Now I see a lot of you are moving on to practice quiz. Before I move on to practice quiz, so it's easier for me to timestamp, are there any other concept question? I'll give it a minute or so to get any other concept questions before I go to quiz 3. You're welcome, Eugene. I do not see any concept questions. Last chance to ask concept question, Arushi. What type of things? Hello, 1.2 and 1.3. I can apply mathematical to compute mass percent. So, quite honestly, Arushi, in LO, 12, not 2. 12 and 13. Let me go to that. Arushi, do you remember that one question where I had the electron spins and I gave you, I think, dipole moments, and I asked you to predict the value? Some weird, funky kind of question. So 12 is like weird question. I don't think you can practice a lot for it. A lot of the 12 will be pattern recognition if there are questions in there. 13 would be, they may give you something about quantum mechanical model, like a student predicts that the energy of transition from S to 1s to 1p will be higher than 1s to 2p or something like that. Is that in accordance with quantum mechanical model? These two are not huge topics. I generally expect multiple choice questions on those. I wish I were more clear than this, but there are not a whole lot of questions on this that I can share with you, Arushi. But a lot of this would be on learning objective 12 and 13 would be pattern recognition. They'll give you all the information and you'll need to read and process that using your understanding. But they will not ask you to recall anything. They'll give you all the information and look for pattern or data in there. Ritu. In the spectrophotometry lab, there is an air bubble that scatters light? Lower, Ritu, because remember, air does not scatter light unless there are large turbid particles like smoke or smog or something is in there. So clear air lets the light go through. So you will have a lower value of molarity because we are looking for molarity of the colored substance. You're welcome, Arushi. Oh, you're so welcome. Totally. That's what I'm here for. Thank you for spending your Sunday evening with me, Elements. Sivani, can you clarify the difference between Bohr model and quantum mechanical one? The biggest difference, Sivani, between Bohr model is Bohr model said there's a nucleus and then there are energy levels around nucleus and electrons within the same energy level all have the same energy. He didn't have the concept of orbitals. He only talked about orbits or energy levels. And hence, all of the electrons were to have the same energy. But quantum mechanical model says that even within the same energy level, energy of electrons could be different. Remember? So in the second energy level, these two are s electrons. I'm just drawing it like this for you to understand. They don't really look like this. And these are p electrons. P electrons are higher energy than s, even though they are both in the second energy level. So quantum mechanical model introduced the concept of orbitals. Okay, Sivani, Ritu. Number 10 and 13 in purple packets. So this is where I might have messed up, and I thought I was being very clever. I don't think I brought the purple package. So, Ritu, you will have to tell me the questions, or on Tuesday, I will be there by 7:30 latest. 7:20 more likely. So you can ask me those questions then. Or if you put on Facebook group, some kind soul will definitely put the answer out for you. You're welcome, Sivani. Eugene, for titration, if one didn't rinse the burette with NaOH and if they were standardizing the solution, molarity will decrease because if you do not rinse with NaOH, my assumption is that you've already rinsed it with DI water. So if you rinsed the burette with DI water without rinsing and then you forgot to rinse with NaOH, when you pour NaOH in there, that DI water that's present in the burette, some might be sticking to the wall or something, that will dilute. So you've diluted, so you will now need sorry, I take it back, Eugene. You've diluted, but you don't know you've diluted. So you'll use a larger amount of your NaOH to neutralize the moles of KHP. So it is the same moles of KHP, same moles of NaOH, and you're getting a larger volume, so molarity will be lesser. Did you see my thought process? So let's say you have 5 moles of KHP in here, right? And if this was actually 1 molar or 0.5 mole, whatever, undiluted, then you should take a certain volume. Let's say you take 5 mils of this. But because you diluted it because of not rinsing, now you're going to take 7 mils of it. It is still equal to 5 moles, right? Because your KHP is the same. And when you divide it by inflated volume, then you will get a lower molarity. Ritu, why the spectrophotometer is not a good... Ritu, so what does spectrophotometry work with? What is the first requirement of spectrophotometry? That it should make colored substance. But first group cations are not colored. Only D block transition metal cations, and that too not all. Only half partly filled D orbital cations make color. So that is the answer for that. Okay, I'm going to move on now, elements, to quiz 3 so I can finish. And Planck's constant is, you're welcome. Planck's constant, Kyle, is a constant that is used in equation E is equal to hc over lambda, or E is equal to h nu. It's got a constant value of 6.2626 times 10 power negative 34 joules second. And you just substitute this to calculate energy of a photon by using either equation. You are welcome, Eugene. Claire, can you explain what makes an ion colored? So an ion that is colored has electron configuration, doesn't matter what is in the S, but it has D1, D2, D3, D4, D6, D7, D8, D9, but not D5 or D10. So basically, these are the ions that have empty spaces. D1, D2, D3, they all have empty spaces. D4, but D5 has every orbital filled. So D5 is not colored. And then D6, now these are empty, so it can come here, D7, D8, D9, but D10 has no empty space. So as you give energy to electrons, as they jump to the D sublevels and come down, they give off energy in the visible range. So our eye sees it as color. You're welcome, everybody. Okay, so quiz questions. You will need to repeat because it's so down on my chat. So can you please rewrite the questions that you want me to do on practice quiz 3? You're welcome, Claire. Practice quiz 3 questions, elements. Ritu, number 2B and 6. Okay. To be or not to be? Haha. Okay. So 2B, Ritu. Calculate the average atomic masses and identify the element. The relative abundance. Relative abundance is 10 for isotope 15 and isotope 29 is 100 and isotope 44 is 80 Oh my goodness, will it ever stop? And isotope 45 is 5. So first we need to add all the relative abundances and change them to percent abundance, because we know that average atomic mass is mass of isotope 1 times decimal fraction of percent abundance, not relative abundance, right? And then you add the next isotope, same thing, and so on. So let's first find what are the relative abundances. So 10, 100, 80, and 5. So when you total it up, you get 195, right? Now let's change it to percent abundance. So it'll be 10 times 100 over 195, right? And you'll use this ratio to convert all of the relative abundances to percent abundances. And then you will get this data, and then you write its decimal fraction, multiply each isotope's mass with the decimal fraction of percent abundance, and add to the second isotope's mass to decimal fraction of its percent abundance, and then get the final mass in AMU. So that is 2B. And then number 6. Number 6 says, given the following graph, what is the best one, right, to absorb wavelength using curve 2? So there are two curves, curve 1, curve 2. So if you look, I'll try and redraw it. It's going down, then goes up, and goes like that. And this is curve 2, and curve 1 is even higher, right? Somewhere. This is curve 2. So there are two criteria for the best wavelength. First is you'll go for the highest absorbance. But if you go to the highest absorbance, yeah, it works. It is the highest absorbance must be less than 1. Because at 1, only 10% of the light is going there, because it's negative log percent transmittance. So 10% light is only reaching the detector. If the value is higher than this, then you will have so much inaccuracy. So you want to choose value of less than 1 with the highest peak. So at the highest peak for curve 2, it is still, absorbance still is less than 1. So we can find the range. So I'll accept any answers between 530 and 560, because both of those are pretty much between that. Okay, 1 and 8. So it'll be very nice if you ask me specific question, what part of it you get, what part you don't get. I can do the entire problem, but then I don't know what part you didn't get, but I will do it. Question number 1 says, which of the following statement clearly aligns with Bohr model? It is D. Electron transition produce discrete wavelengths, hence discrete energy, providing an evidence for quantization of energy for different energy level. So Bohr talked about that electrons go around nucleus in different quantized energy levels. So as long as electrons moving in one energy level, its energy stays the same and doesn't change. But if it absorbs energy and goes to higher energy level, then it will keep going till it absorbs again. Or if it drops down, then it gives off energy. Let's see why other options are not right. Part A says the farther the electron is, the lesser is its chance to leave the orbit. That is not right. You know, the farther the electron is, the easier it can leave, because there's less attraction from nuclear protons. Let's look at B. Electrons are able to absorb IR radiation for transition. We just talked about it. Electronic transition require higher energy like UV. C. Once excited by an incident photon or heat or electricity, electron can stay in excited state forever. No, electrons don't stay in excited state. They always want to come down to ground energy level. So you know that number 1, only correct answer is D. Number 8 is what Sivani asked, right? 1 and 8. Consider the particulate level drawing below. Draw the particulate level drawing using appropriate ratios. Okay, so this one shows you a particulate level drawing of a reaction where you have CH4, AC, and HH, right? You have 1, 2, 3, 4, 5 CH4s, and you have 4 oxygen, right? And the reaction will have to be given to you. I hope that wasn't your question. So I will give you the reaction which says CH4 plus O2 gives you CO2 plus H2O. And now, if you say, so there are 5 CH4s here, right? And there are 4 O2s, correct? So, you know they react. So you'll have to balance this equation. When you balance it, you put a 2 here, and then you put a 2 here, and does that balance it? I think so. So when you balance the equation, then you realize that they react in a 1 to 2 mole ratio, and you will only make, so there are 4 oxygen, right? 2, 4. So you have 1, 2, 3, 4 oxygen. So 1, 2, 3, 4 CH4 will be converted. So how many CO2s you will make? You will make half of those CO2s. So that will be 2 CO2s. Let me read it. I'm confusing you more. This one. It says consider, draw the particulate level drawing indicating appropriate mole ratios if it went to completion and formed CO2 and H2O. So yeah, oh goodness, this is O2. Okay, so then O2. So there needs to be a 2. This is balanced, right? CO2 to H2O. Okay. So you will have, I'm going to redo it. I'm sorry, Sivani, if I confused you more. Let's start over again. Okay, so there are 5 CH4s given to you and 4 O2s given to you. And you know they react in a 2 to 1 mole ratio. So for 4, you need 8, but you don't have 8, right? How many do you have? You have, so for 2, you use 1 CH4. For 2, you use 1 CH4. So all that is gone is all of this. So what is remaining? You have 3 of the CH4s, right? Because they are remaining. And you will make half of the O2s, right? 2 to 1 ratio. So half of the O2s in CO2. So you would make 2 CO2, and then you will make 4 waters because you make double that water. So you just have to kind of see the mole ratios there and do that. So number 8, I just did. Aya is asking number 8 in practice quiz. So this is the number 8. So in number 8 elements, I will give you this equation. The equation I gave you was not balanced, so you have to balance it, right? Make sure that your atoms on both sides are equal. So then you get the balanced equation, and then you realize that 2 oxygen react with 1 CH4. So you can cross them out, and after that you have these leftover CH4, and then form CO2 and H2O. Yeah, the scale is off. When I write these questions, some of them, Ritu, I just am confined by the pictures I can find on Google Images. So that is why it looks weird. So don't worry about that. So Claire, yes, if the height of peak went over 1, then I will choose the next wavelength that keeps it below 1. That is correct. For number 2A, why is C correct? I am showing B. Are you showing C in your answer document? Ritu, can you please check? Okay. Aya, why does the most abundant isotope have to be set to 100? So, Aya, that is because now you need to find the ratio out of 100. So I would just say the best way is add up all of the relative masses and then try and find the ratio. If out of 194, it is 27, then out of 100, how much would that be? Because percent abundance is out of 100. Hello, Nishant. Yes, that is very right, Nishant. You need to write a one-line explanation for why your answer is the correct answer. And that does add a little bit of a challenge, but that you have to do. You're welcome, Claire. Ritu, oh no, I asked why C is incorrect. Okay, let me go over it. So number 2 says, diagram below shows the mass spectrum of sample of an element. Which of the following statements is true? Okay, the average atomic mass will be close to 29 because it's no. So this is a weighted average, Ritu. So the average atomic mass will be the average of 29 and 44 peak, because if you see, both of them are present in pretty high abundance. If there was only one peak that was high and rest all were very low abundance, then you could say that the average atomic mass will reflect the longest peak. But if 2 of them have pretty high abundances, then you couldn't say which it will be closest to, because it'll be the average of the 2. Claire, could you explain how to read the graduated cylinder in 10C? Okay. So Claire, in 10C, it is not a cylinder, but it's shown a burette, I think. Or it could be, it doesn't have to be, but whatever it is, let's draw it. So it is 10C I'm doing on the practice quiz. So what they have is they have 27 over here, and then they have 28 over here, and it's 1, 2, 3, 4, and then fifth one, 1, 2, 3, 4. Okay, my markings are not very even. This is where it is, and it is at the second after that. So it is right here. Okay, so if this is 27 and this is 28, so this is 27.1, 27.2, 27.3, 4, 5, 6, 7. So this is at 27.7, right? But if you read here, you are certain that it is greater than 27.7 and it is lesser than 27.8, right? So you have certainty in the 10th place. So it's reading will be all certain digits plus the first uncertain digit. So its reading will be 27.70 mils, 27.71, 72. I'll take any of those answers. I would be looking for the second place of decimal, Claire. You guys are welcome, and it is 8:54 elements. Last question. Any last questions, elements? Okay, Claire. No, the way you read it, so this is assuming that you started at 0, Claire. So we assume you started at 0. That's an assumption. So what I'm looking for is the second place of decimal here. And there could be minor differences in where you see the meniscus. Some may see between 27.7 and 27.8. Nobody will read it greater than 27.8. Nobody should read it less than 27.7. So between 27.7 and 27.8, I will accept any values as long as they are to the second place of decimal. So I'm looking for the second place of decimal here. Okay, Nicole. Yes, you will totally use the same technique with pipettes as well because you're delivering the solution this way. That is correct, Nicole. Okay, 3 minutes to go, elements. The units for nu or frequency, Ritu, are 1/second or 1/minute or 1/hour, or we call it Hz or Hertz. Hertz is same as 1/second. Yes, Nishan, that is correct. So in this one, there will be 4 sig figs. 1, 2, 3, 4. Raghav, for question like number 8, you may be given balanced or you may be given unbalanced. So if I'm drawing particulate level drawing, I want you to be able to count the atoms on left and right. So you could have used mole ratios or see how many will react and then draw the leftovers. So that's fine too. Arushi, Planck's constant and the light equations are on the equation sheet. I had you guys look at it the other day, so you don't need to. You're welcome, Nishant. You're welcome, Raghav. Alrighty, elements, is going to be that time. It's 8:59. Save rest of your questions for tomorrow's study session. Tomorrow, I'm going to be going over Big Idea 1 practice test, and I'll do question and answers from there. So I hope to see you tomorrow. I add the study session here at home. I won't be in the classroom tomorrow, but elements, make good use of your time. Please do not waste time. Okay? Alrighty, elements. I will see you virtually again tomorrow night at 8 p.m. for the study session. You are all so welcome. Thank you very much for spending your evening with me. I appreciate all those likes. Good night, elements.